This presentation is regarding solar energy. It's a part 2. Part 1 already explained in the previous presentation. Now let us see the definition regarding solar constant. Solar constant, and we'll see it is the amount of incoming solar electromagnetic radiation per unit area that would be incident on the plane perpendicular to the rays. That is, this is the sun, this is the earth, this is the starting of the atmosphere, and perpendicular to this one, how much radiation is falling on this one per unit area. That is at a distance of 1 AU, we call it that. Astronomical unit means AU. That distance is approximately 149.5 million kilometer from the sun to the starting of the atmosphere. The distance is this much. What is the solar radiation per unit area? That is what we call it as solar constant. Approximately it is 1366 watts per meter square or 1.366 kilowatt per meter square. Approximate value only, but here it is shown as 1.1360 watts per meter square. So approximated value, that one. Therefore, the solar constant includes all types of solar radiation, not just the visible light. All the radiations coming, not only the solar, visible light, all the radiation comes. What is perpendicular to this one? How much is the radiation per unit area? That is equal to 1366 watts per meter square. That is the solar constant. Continuing the concept of solar constant, from the solar radiation spectrum, which is a plot of solar radiance, that is watts per meter square per nanometer versus wavelength. That's already we have seen in the other presentation, part 1. And this is the spectral distribution for different wavelengths. This is the yellow one is called the sunlight at the top of the atmosphere, and the red one shows the top of the sea level or the earth. Therefore, the difference of that one is the radiation absorbed that one. And therefore, the area under the curve gives the total area intensity, and it is approximately 1.366 kilowatt per meter square. That is the solar constant. And in this context, let us define a commonly used term that's called the solar constant. The sun-earth distance varies about the mean distance around 1.7%. That distance will vary, and mean we will be taking as 149.5 million kilometer, which is known as 1 AU. That is astronomical unit, we call it as. And the solar flux outside the earth atmosphere is 1.366 kilowatt per meter square, which is known as, which quantities we call it as solar constant. Continuing the solar constant, it can also be seen that as solar radiation makes its way towards the Earth's surface, some of it is being absorbed by various constituents in the atmosphere, giving terrestrial spectrum and irregular bumpy stripe. That is an irregular bumpy stripe. That is this typical solar spectrum at the top of the atmosphere. That is the top of the atmosphere is that, what is the yellow one? Top of the atmosphere and the sea level, that is the red one. And the difference is the radiation absorbed or scattered by the atmosphere. The difference of this yellow and this red, that difference of this one is the radiation that is absorbed or scattered by the atmosphere. The spectrum of the black body at 5800 degrees centigrade is also superimposed. Therefore, this is the solar radiation spectrum. Therefore, continuing the solar constant, also shown are the area under the actual solar spectrum that corresponds to, that is area under that showing this is called the visible region, and this is called the infrared region, this is called ultraviolet region. The area under this one, that is within that one, is infrared region 46%, visible 47%, UV 7% portion of the spectrum. The visible spectrum which lies in this UV and IR ranges, that is 0.38 micrometer, and to wavelength is 0.78 micrometer. Therefore, the area under this one that indicates the solar constant. Now let us see what do you mean by solstice. That is during June 21 to 22. The sun is, this is the earth movement for different, months here. Therefore, June 21 or June 22, here, this position of the earth, this is the sun here. During that period, earth is positioned in the orbit so that North Pole is leaning 23.5 degree towards the sun. This is the position during June 21 to 22. And all location that during this period, all the locations northern of the equator will have day length will be more greater than 12 hours, while the location on the south, that is southern side of the equator, that will have a day length less than 12 hours. That is here, that is June 21 to 22, that India is laying in the northern side. Therefore, during this period, we'll have more day than daytime than night. Now, on December 21 and to 22, that is this position here, during that is winter solstice, Earth is positioned, so that South Pole is leaning 23.5 degree towards the sun. This is the position, 23.5 degree. And in this case, here during this period, all the location northern of equator have day lengths less than the 12 hours, while all location southern of the equator have length exceeding the 12 hours. For as far as India is concerned, during this period, that is during this 21 to 22 December, there will be length of the day will be less and length of the night period is more. For that, we call it as solstice of the duration of the months as such. Length of the day and night will not be equal during this period. Another word is that, or the things to be considered is equinox. That is during this period, equinox here, that is happens during September 22 23 and March 22 21. Here March 22 21 and September, that during that period, both day and night periods are equal, that be 12 hours. Therefore, on 22 and 23, also called autumnal equinoxes in the northern hemisphere, neither pole is tilted towards the or away from the sun. Therefore, during that period, daytime will be equal to the both will be 12 hours. And here in northern hemisphere, that is March 22 21, during that period, the arrival of the vernal equinoxes or spring, when once again the poles are not tilted towards or away from the sun. During this period, that is September 22 23 and March 20 and 21. During this period, day length of both these days, day length on both of these days, regardless of the latitudes, are exactly 12 hours. In both cases, 12 hours, or day and night will be equal in these two cases. And here it will be, one will be extreme more, another will be less. That is, so that is called equinox. Now let us analyze one more, spectral distribution of the solar radiation. Solar radiation consists of different radiation having different wavelengths as such. And wavelength, that is shown as here, this picture as such. Here, this is the visible region, and this is the ultraviolet region. This is the infrared region, then X-rays, gamma rays, like that, microwave, etc. These have been shown at different wavelengths of the spectral. And here, in this one, the solar radiation spectrum is close to that of a black body with a temperature of 5800 Kelvin. For same as already we explained that one. Here the spectrum of the electromagnetic radiation striking Earth atmosphere is 100 to 10⁶ nanometer. Therefore, this is again, we have already seen that one. This is at the top of the atmosphere, and this is the top of the sea level. This one, the difference is the absorbed one, and that absorption is because of the different, elements like H2O, CO, CO2, like different particles in the atmosphere that is getting absorbed and or scattered, and what available is that what the shown in the red color. So this is the spectral distribution of the solar radiation. In the radiation coming to the Earth, it has got two components as such. One we call it as direct radiation, other one is called diffuse radiation. Direct radiation is also called beam radiation. That is a solar radiation that does not get absorbed or scattered but reaches the ground directly from the sun. That directly, this is called a direct radiation. Directly that coming to the earth as such. But it produces shadow when interrupted by an opaque object, and that produces a shadow. This direct radiation produces a shadow. And here, second part is called diffuse radiation. Diffuse radiation is that solar radiation received after its direction has been changed by reflection or scattering, either by scattering or by reflection in the atmosphere. Due to that one, that part of light, what we call it as diffuse radiation. This is called the diffuse radiation. This one and this one, diffuse radiation, and this is called the direct radiation. Therefore, this is a two part of the radiation coming to the earth from the sun. One we call it as direct radiation or beam radiation. Second one is called diffuse radiation. That involves both scattered one as well as a reflected one. This give a pictorial representation of how the sun rays are reaching to the earth's surface as such. For one part is directly coming. This is a direct beam, or this is called direct radiation, or this beam radiation. This is directly coming that one. Certain portion there are porous atmosphere. This region is called extraterrestrial region at the top of the atmosphere, and this is called terrestrial region. And when this region consists porous atmosphere and O3, O2, H2O, CO2, dust, etc. These are all in the porous atmosphere comes. And after here, this region. This is called the terrestrial region. Therefore, here this one is the diffuse radiation. After diffuse, scattered and diffuse radiation is coming. Diffuse radiation and the beam radiation is the total radiation that comes to the earth. And here the reflected back to the space, certain portion is reflected back. And what is on this one, what is reaching on the earth's surface is the sum of the beam radiation and the diffuse radiation. Now let us see another term to be explained here. Air mass ratio, AMR, we call it air mass ratio as such. Air mass ratio means the terrestrial spectrum also depends upon how much atmosphere the radiation has to pass through to reach the surface, how much it is to length to pass that one. As shown in the figure below, under the simple assumption of the flat earth, we are assuming that earth is a flat assumption. The air mass ratio can be expressed as this ratio here. Ratio here it is represented as H2 by H1. H2, this is a H2 and this is equal to H1, where H2 is the path through which the atmosphere to reach the spot on the surface. That is, it is from the sunlight, it has to reach that. This length is called to H2. And H1 is the path length through the atmosphere with a sun directly overhead. That is, this length is equal to H1. Therefore, this H1 is less than H2. And this ratio, H2 by H1, that ratio we call it as air mass ratio, always that will be more than 1 as such. Therefore, another way, the same thing can be in mathematical form, it can be explained as this is equal to sine beta equal to H1. If you see that one, sine beta equal to H1 by H2, or H2 by H1 equal to 1 by sine beta. Therefore, the air mass ratio M equal to H2 by H1, which is equal to 1 by sine beta, where this is at this angle beta. Beta is the altitude angle of the sun as shown in the figure. This is the beta angle. 1 by sine beta is equal to air mass ratio. Continuing the air mass ratio concept here, if the air mass ratio is equal to 1, it means that H2 by H1 equal to 1, or H2 equal to H1. That means that sun is directly overhead. Once sun is directly overhead, H2 equal to H1 and the air mass ratio equal to 1. That is, AM0 means that no atmosphere, that is, it's extraterrestrial solar region. By convention, AM0 means that no atmosphere, that is, it is extraterrestrial solar spectrum. Often, an air mass ratio of 1.5 is assumed as an average solar spectrum at the Earth's surface. That is, an air mass ratio 1.5 is assumed as average solar. Standard testing condition will be taking as air mass ratio as 1.5. Air mass ratio equal to 1.5 means that Sine beta equal to 1 by sine 1 by 1.5, or beta is equal, approximately you can calculate, is equal to 42 degree. That is beta equal to 42 degree. Therefore, as sunlight passes through more and more atmosphere, that is, as air mass ratio increases, means H2 increases, because it is that beta is reducing. If it is beta is reduces, it has to pass through more area. Therefore, as air mass ratio increases, less energy arrives at the Earth's surface and the spectrum shifts somewhat towards the longer wavelength. That is the effect of air mass ratio. Therefore, as sunlight passes through the more and more atmosphere, that happens when the air mass ratio increases, less energy will be arriving at the Earth's surface and spectrum shifts somewhat towards the longer wavelength. Now let us see the solar spectrum variation with air mass ratio. Therefore, as the sunlight passes through more and more atmosphere, that is, as air mass ratio increases, less energy will be arriving at the Earth's surface and the spectrum shifts towards longer wavelength. This impact on the atmosphere on incoming solar radiation for various air mass ratio is shown in the figure. Therefore, here, as the spectrum has that one, this is the outside the atmosphere where m equal to 0, but at the surface of the atmosphere, so at the surface of the earth, here with m equal to 1, that is air mass ratio equal to 1, this is the energy coming here. But as m increases, we can say that the amount of energy that is coming is getting reduced. Therefore, the solar spectrum for extraterrestrial, that is m equal to 0, solar spectrum for sun directly overhead, m equal to 1, and at the surface with a sun low at the sky when m equal to 5, m equal to 1, m equal to 1 means that it is directly at the overhead, and here m equal to 5 as such, here and at the surface with a sun with a low in the sky, that is sun low at the sky, in the sense m equal to 5, where air mass ratio is large. Therefore, the amount of spectrum that is coming, solar energy coming, is getting reduced as well. Therefore, this shows the variation of the solar spectrum for different air mass ratio. This is m equal to 0, this is m equal to 1, this is m equal to 5. Now let us see the Earth's orbit around the sun. This is the sun, Earth orbit, Earth is moving, and the Earth revolves around the sun in an elliptical orbit every 365.25 days, making one rotation a day around its own. In a day, its own is north-south axis as such. Therefore, the eccentricity of the ellipse is small. This eccentricity is very small as such. The point at which the Earth is nearest to the sun, that is called the perihelion, occurs on January 2nd, at which the point it is a little over 147 million kilometers away. At the other extreme, aphelion, which occurs on July 3, that comes July 3, the Earth is about 152 million kilometers from the sun. The tilt of the Earth's spin axis with respect to the eclipse plane is what causes our seasons. For different seasons comes because of that one. So this is the Earth orbit around the sun, pictorial representation. There is a term to be defined as solar declination, delta, solar declination. Solar declination, you can see that one here, the angle, but is the delta angle. This one angle is delta. Solar declination can be defined as the angle between the line joining the centers of the sun and earth, centers of the earth and sun. That's this line joining the centers and earth and its projection on the equatorial plane. Its projection on the equatorial plane means this one. For this angle, we call it as delta. That is projection on the equatorial plane. That is called the solar declination. The solar declination changes mainly due to the rotation of the Earth about an axis. its maximum value is equal to plus 23.45 degrees, and that's on December 21st, and minimum is minus 23.45 degrees, that's on June 21st. That is this angle we call it as solar declination delta. Conventional sun-centered view of the sun-earth system, that is shown here. This is the sun and this is earth for different months here. Here June 2nd, here is a March, June 21st, March 22nd, December 22nd, March, September 23, like that. The this earth position and this is a sun position. And here we see that angle, declination angle here is equal to delta equal to 0, and here declination angle equal to minus 23.5, and here delta equal to plus 23.5, and here also declination angle equal to 0 for different duration that happens this one. Therefore, the solar path is highest over the North Pole with a the sun rise making delta equal to 23.5, here 23.5 angle with the plane of the equator around that happens around June 21st. Around September 23 and March 22, that is these two cases, the sun's path is parallel to the earth, that is the sun path is parallel to earth's equatorial plane, and the sun rays parallel to the equatorial plane, and the sun rays arrive parallel to the equatorial plane during this period. And around this December 22nd, the solar path is lowest below the south pole, making the angle delta equal to minus 23.5 degree angle with the equatorial plane. For different periods this or months, the delta is changing here. Here delta equal to plus 23.5, here minus 23.5, here equal to 0, and here 0.